Math 1314, Tyler Junior College, Section 2.1, Basics of Functions and Their Graphs, the vertical line test. In the previous videos, we've defined a function and we've shown how to take a function written in function notation and sketch its graph by generating ordered pairs and connecting them. What I neglected to mention is that any graph is a relation. In the video about equations, I mentioned that any equation is a relation because it can be used to generate ordered pairs. Or equivalently, we can check to see if an ordered pair makes the equation true. If so, it belongs to that relation, otherwise it does not. But graphs are also relations. Why? Because just like equations, a graph implies ordered pairs. For example, let's take a look at this twisty graph over here. Although the x and y axis are not marked, let's pretend they were. If I pick any point on that graph, there's an ordered pair associated with it. There's an ordered pair, there's an ordered pair, there's an ordered pair, there's an ordered pair, there's an ordered pair. And there's a lot of them. There's an infinite number of them. This point, however, is not on the graph and therefore is not part of the relation, nor is that one, or that one. So if you have a graph, you can view it as a relation because every point on it is an ordered pair or has an ordered pair associated with it. So if you have a graph, it is fair to ask things that you ask other relations, such as domain, range, and are you a function? In this video, we're going to address the question, when does a graph represent a function of x? You may already know how to do these if you remember something called the vertical line test. But I want to appeal to your intuition for a second and ask you, of these, which ones do you think are functions and which ones do you think are not? And when I say functions, I mean functions of x, for those of you following the calculus discussions I'm having. B is not a function of x. Here's why. What breaks a function? What has to happen in order for something to not be a function? According to the definition of a function, you're a function if every element in the domain is paired with exactly one element in the range, or in terms of x's and y's, if every x is paired with exactly one y. So to break being a function, I have to find an x that's paired with more than one y. I can find them on the second graph. For example, let's go over to this number and let's just say it's 5 for the sake of discussion. The point on the graph above it has an x coordinate of 5. And some y coordinate, let's just say it's 3. So over 5 up 3. But if I go below the 5, there's another point. 5, comma, let's just say -3. Just making up these pairs. So it seems that I found evidence to violate the definition of a function. I found an x value with 2 y values, and honestly, the numbers I wrote were arbitrary. I didn't even need them. I know these 2 points have the same x value. Why? Because they're directly above each other. And I know they have different y values. How do I know that? Move this over a little bit. How do I know they have different y values? Because one of them's higher than the other. So if I were to connect these dots, well, let's go ahead and extend this vertical line. If I drew this vertical line through this graph, because it intersects the graph twice, that means I have located 2 points that violate the definition of the function. They have the same x but different y values. Now, that's not the same case. That's not the case on this one. I cannot locate 2 points with the same x value but different y values, because if I were to drop a vertical line, say here, it would only cross the graph once. That is the only point on this graph whose x coordinate is whatever number is here. Maybe it's 2, maybe it's 1, but it doesn't matter. It's the only point above that x. And no matter where I drop a vertical line, I can't hit it twice like I did on that one. So this leads to a test of a graph to see it's a function called the vertical line test. And the vertical line test goes something like this. A graph represents a function, parentheses, of x. And again, in our class, functions will always be functions of x. I only say that because I know that for those of you going to calculus, there are functions of y. A graph represents a function of x if and only if, meaning that not only will this vertical line thing show you our function, it will also show you or not. If and only if a vertical line cannot cross a graph more than once. So, if a vertical line cannot cross a graph more than once, like this first graph, no matter where I drop a vertical line through it, it's only going to hit the graph once. So if a vertical line cannot cross a graph more than once, then you're a function. I cannot cross this graph more than once with a vertical line. Now, if and only if also means, well, basically here's what if and only if means from a logic perspective. These two statements are either simultaneously true or simultaneously false. Meaning if one is true, the other is true, and if one is false, the other is false. So what this implies is if you can cross a graph more than once, then you're not a function. So it works both ways. Cross once, you're only a function. Cross twice, you're not. So what about this one? Grab a vertical line. Can you put a vertical line anywhere here that crosses it more than once? Despite all the twists, the answer is no. Once, cross only once, cross only once, cross only once, and every other vertical line. So the answer to which of the following graphs represent functions: A is a function, it passes the vertical line test. B is not a function, it fails the vertical line test. And C is a function, it passes the vertical line test. So the vertical line test is one of the easiest things ever. You just got to remember what to say under what circumstances. If you can only cross the graph once, no matter where, you're a function. But at any point, if you can cross it twice, you're not a function. Now, I'm about to put this in the context of functions of y for the benefit of those of you going to calculus. So at this point, if you know you're not going to calculus, you can stop watching and you'll be okay for college algebra. But if you're curious, I would listen. If we wanted to think of these as functions of y, then basically we just have to switch everything. A graph represents a function of y. Well, remember, to be a function of y, every y has to be paired with exactly one x. Only one of these graphs is a function of y. And if you watch the previous video, you know it's this one. So why are the other two not functions of y? Well, let's take a look at A. To be a function of y, every y has to have exactly one x. Remember, we're just switching who's the range and who's the domain. If I go to a y value on this graph and go left or right, then I found 2 points that have the same y value but multiple x values. That violates the definition of being a function of y. So instead of the vertical line test, it's the horizontal line test. Or rather, I should say, it's a horizontal line test. A graph represents a function of y if and only if a horizontal line cannot cross a graph more than once. In this class, there is another test called the horizontal line test that answers a different question for functions of x. But for functions of y, the horizontal line test answers the question, are you a function of y? So, not a function of y, crosses more than once. Function of y doesn't cross more than once. Not a function of y. This one fails miserably. I can shoot a horizontal line that crosses it 1, 2, 3, 4, 5, 6, 7 times. again, but for college algebra, you only need to worry about the vertical line test, determining if a graph is a function of x.